Let's now shift our focus to one of the most transformative concepts in industrial Internet of Things, digital twin. So it all started back in 2011 when the idea of a digital twin was proposed to simulate and predict the structural behavior of aircrafts by modeling its real-time behavior on a digital replica. Uh, just a year later, NASA formally defined digital twin as integrated multi-physics, multi-scale probabilistic simulation of a vehicle or a system that uses the best available physical models, sensor updates, fleet history, and so forth to mirror the life of its flying train. So that means we now use data from the sensors, simulation, and historical insights to mirror the real-time condition and performance of physical systems. So either it is a machine or pipeline or a factory floor. So with the rise of machine learning and wireless networks and cloud computing, digital twins move from concept to reality, fueling innovation in predictive maintenance, asset optimization, and smart manufacturing. So today, many researchers define digital twin as nothing short of like next generation simulation, next generation of simulation, but more like a dynamic, real time, and an intelligent system. So let's go a step further into the digital twin concept and understand how it shapes the real world IoT applications. So initially, digital twin technology was used for mainly for product design and 3D prototyping. We could simulate the physical design of the product before manufacturing it. But as more and more physical objects started generating sensor data, digital twins evolved, and they broke out of the design room and stepped into the heart of IIoT, AI, data analytics. So giving the industries the real-time control and predictive analytics. So with digital replica of a physical object, whether it's a pump, turbine, or a machine, we can run what if scenarios. This is the most important thing, to check the performance in different conditions and optimize systems without touching the actual device. So today, digital twins are used across multiple sectors. So these sectors are renewable energy system, renewable energy, in which we can simulate the wind farms to optimize the power generation, mechanical systems where we can do fault diagnostics, degradation tracking, and scenario testing. In oil and gas, we can improve the efficiency in power generation plants, chemistry for tuning or improving the chemical processes and increasing the yield and efficiency, aviation, ensuring that the system stays compliant with the evolving regulation and safe. So this is like a game changer for predictive maintenance operations and controls in the IoT environments, where the real-time data drives the smarter decisions. So digital twin is very suitable for our core of the IoT. So in the world of IoT, many people confuse the digital twins with the simple simulations. But digital twin is more than just a model. It's a real time digital replica of a physical systems. Unlike simulation, which only answer what if. Okay, normal simulations, they answer only what ifs scenario. A digital twin mirrors what is happening now, and because it receives the real data from the actual system, this connection between the cyberspace and physical space is what makes a digital twin truly powerful. So digital twins are really powerful if it is a real digital twin. So industrial settings such as like manufacturing, Um, this means that we are doing some monitoring, diagnostics, control, and predictive maintenance, not just analyzing hypothetical outcomes. So the fidelity and the live synchronization are the key differentiators. So we should remember that a simulation, uh, we should say simulation images, okay, while digital twin reflects reality as it happens. Okay. Okay. So in the world of industrial systems, we often hear, um, before we were calling it something cyber physical systems, CPS, and and IoT. While all these three, all of these, they use sensors and networking technologies, but they have like a distinct role. Uh, we will see in the next slide. CPS is more comprehensive. It's a fusion of cyber world and physical world, and it includes the physical assets as a digital twin and the control feedback loop. So when we say CPS, cyber physical system, we mean the complete system. It contains the hardware and the software, all of it. Okay, so hardware and software and the real-time interaction. This is CPS, cyber physical systems. A digital twin, on the other hand, is only the uh, a digital uh, representation, and it reflects the state behavior of the physical system assets, but does not operate independently. So it needs its physical counterpart. Think of it like a digital brain, but it's not the body. Okay, and now the IIoT, it enables the communication. Uh, it connects the physical assets and allow the data to flow, but it does not model the assets or create the digital representation. So that's why we use IoT. We say that IoT is a infrastructure, whereas digital technology is the IoT. We can say that IoT is infrastructure. IoT is infrastructure, while digital twin is intelligence, and the CPS is full full smart system. Okay, and in summary, we can say that the IoT stands for takes care of connectivity. Digital twin is digital model, and CPS is the integrated smart system. Okay, all right. So in next slide, we will see in detail here. So let's now look at a closer look at how digital twin, CPS, and IoT interact visually. On the we see that the physical, on this bottom half, we see that the physical world, and this is where the actual machines are operating, such as like robotic arms, CNC machines, and conveyor robotic arms, etc. machines, CNC machines, for example, CNC machines, computer numerical control machines. So So at the bottom we see the physical assets, all the physical assets. On this top half we see that the cyber world, and here we see the digital twin is residing here, which is the real-time virtual model of those machines. Okay, so and uh, and these twins simulate the performance. Okay, so we have like a virtual but real-time models, and what they do is they actually simulate performance. They even predict issues, okay, based on based on a real-time condition of this real system. And the IoT layer, this one, the IoT layer uh, connects these physical uh, assets. Okay, so in this IoT layer, it is basically connecting all of these physical uh, machines, these physical machines, and they take it to your cyberspace. So this is what the IoT is doing. Okay, so what IoT layer? The IoT layer connects these physical machines to the digital space. Okay. Sensors, actuators, and connectivity protocols, they send data from machines to their digital counterparts. And the CPS layer, this is the this the this is the CPS layer in orange. This is the CPS layer. So this CPS layer, Cyber Physical Systems layer, uh, is the integration layer where the cyber digital twin and the physical system are interacting intelligently. Okay, so CPS is providing the layer where the cyber, or what you call digital twin, and physical systems interact intelligently. Okay, so this is the foundation of smart factories, and which combines the automation, analytics, and the feedback loops. So in summary, IoT is connecting the physical to the digital world. Digital twins provide the real-time virtual representation, and CPS indicates both of for the autonomous and optimized control. Okay, right. So to technically build a digital twin, there are three core components must be integrated, and they work together. Um, the first one is the information model. This is like a blueprint, and it captures all the specification of the physical assets, dimensions, behavior, and material properties, operation logic, and it defines what the digital twin should represent. Okay, so it defines it defines what the digital twin DT should uh, represent. Then we have the communication mechanism. This enables real-time bidirectional data transfer, data flow between the physical object and the digital counterpart. And we can think of it as like a nerve system using the IoT protocols and sensors and the secure network to keep both worlds in sync. Okay, so and then we have the data processing module. This component collects and analyzes and also the interpret the live data. So it handles the large heterogeneous sources, sensors, and logs and cloud streams, and help make the digital twin dynamic and intelligent. This is the data processing module that we mostly discuss. So here we have basically the real-time status and anomaly detection, real-time uh, status, and also the anomaly detection and I may have predictive actions or prediction happens here. So mainly the three key components sort of they work together. So these are the three layers: information modeling, real-time communication, and the data processing. They form the technical foundation of these three components form technical foundation of any digital twin implementation. Okay, and this is how we are also approaching our project. Okay, slide 44. This is the last slide on this digital twin, and then we will do last video lecture on an example of our digital twin. So in this slide, we highlight that how digital twins are applied across different manufacturing industries. We have taken through some references. Each row shows one real world example, okay, from the research papers, and the object model, the information, the type of digital, the application, physical object, information data processing, data communication standards, and the purpose. So in the first example, it's a factory production line. Okay, so this is example one. We have a factory and a production line, and here a proprietary 3D model is used to simulate the entire production line. Let me write few words here as I speak. So the proprietary 3D model is used to model or simulate the production line. Okay, and the communication is via Ethernet and OPC, and the purpose or goal is to provide a support system level decisions, whether it's design changes or evaluating alternative solutions. Okay, so this is one example of digital twin. Second row is the industrial work cell, and it uses a robot, URDF and SDF. These are common in robotics terminologies. The data flows through the TCP/IP Modbus and Ethernet IP. It gives us the flexible simulation framework communication, and this especially is useful for in modular or reconfigurable work cells. Okay, the third example talks about welding production line, and in this welding production line, a CAD model is with OPC gives a full digital twin for the life cycle management. Okay, so that will help us in the monitoring maintenance and upgrade decisions. They all can be done in the real time. Example 4 is about a 3D printer. It uses MT Connect. This is an open standard for CNC machines, CNC, and other manufacturing equipment. So the focus is on the cloud-based cyber physical manufacturing system, which is ideal for smart factory and IoT integration. So the key takeaways, we can say that these examples show that digital twins are not just simulations, they are live data connected systems powered by protocols like OPC, UA, Modbus, MT Connect, and this makes them foundational for IIoT systems where the real-time monitoring, control, and optimizations are required in the industry. Okay, so thank you very much. I will stop it here, and then we will be left with only one last video that I will record next. Thank you very much.